Okay. Hi, everyone, and thank you for the opportunity to speak here today on our project on the NexGen system, in which we are looking at diffusion imaging of the cranial nerves. I am Yasmin, and together with Beck, I am leading this project. We are working normally over here at the Melbourne Brain Center Imaging Unit, which is located in beautiful Melbourne in Australia. And sorry that we're recording this and not presenting in person. It's already Saturday morning over here, and we thought it'd be easier to record this peacefully without family in the background and one day earlier. So we're located right on the campus of the University of Melbourne, and we do have an older generation 70 system on our side. So we do a fair bit of clinically driven research over here, and so we're familiar with ultra-high field and how challenging it can be to image certain areas of the brain. Because of that, we were very excited about the opportunity to explore the improvements that are available on the NexGen system over at UC Berkeley. And together with clinical colleagues from over here in Melbourne, as well as in Sydney, we've applied for one of the U24 dissemination projects and wanted to explore diffusion imaging of the cranial nerves to see if we can gain some more insight into their internal structure and organization. Our aim was to mostly look at two nerves in particular, that is the CN5, the trigeminal nerve, and CN8, the auditory nerve. Our clinical colleagues are very excited to look about or to study them more deeply and get some form of mesoscale details via diffusion. But it's a very challenging imaging target. Just a quick background on the anatomy of these nerves. So on the left here, you can see an overview of the cranial nerves at the base of the brain. And the two nerves that we are focusing on are the trigeminal nerve, which you can see here in red. A clearer depiction is up here, where you can see that it also branches into three divisions. And the other nerve we would like to investigate is the auditory nerve, which you can see down here in blue. Together with the optic nerve up here in green, they are relatively big, well, comparatively big nerve bundles. And this is one of the reasons why they're actually one of the more commonly imaged cranial nerves. They are clinically quite valuable, especially when you want to understand conditions affecting facial sensation, hearing, or balance. And there is still a lot of potential to learn more about their internal structure and organization using advanced imaging. This is why we wanted to explore high-resolution diffusion MRI. We were hoping that it can give us some more detailed information about the structure of these nerve bundles. However, as I said before, this remains a very challenging imaging target, given the location and also the complex shape of these nerves. You can see this from the anatomical context here. So here we are seeing two T2 axial images. The one on the left is showing us the trigem nerve. You can see that here with the arrows. And on the right, we can see the auditory nerve. The auditory nerve is very close to the temporal lobes, and there's also the mastoid air cells, which you can see here. And on the trigeminal nerve, we were challenged by the proximity to the sphenoid sinus. So all these air-filled spaces create a lot of susceptibility issues for us, and that's why it's obviously quite challenging in general, and especially in diffusion. So in this work, we looked at whether we could overcome parts of this by using the impulse height-only gradient system of the NexGen 70 scanner. The idea was that faster diffusion encoding and obviously a concomitantly shorter echo time would help to boost not just the signal, but also reduce susceptibility-related artifacts and hopefully allow us to get a good diffusion signal from these very small cranial nerves. We've only started scanning. So at the moment, we are still identifying the best acquisition setup, but so far we've scanned two subjects on two different systems. So our local system, which is a 70 plus Siemens system, where we scan with an 8 transmits 32 receive channel Nova head coil. And we have had a different subject scanned. That was, the one on the 70 plus was a 21-year-old female, and on the NexGen system, we've scanned a 41-year-old male. So again, this was done with the impulse edition of the NexGen scanner and a custom-built 8 transmits 64 receive channel head coil. For both subjects, we acquired axial diffusion data with a sub-millimeter isotopic resolution, and we acquired 128 slices across 100, and we acquired 103 diffusion direction across multiple B shells from B0 to B3000. So down here, you can see the important imaging parameters for the 70 plus and the NexGen system. So the parameters for subject 1 were used as a starting point. So subject 1 was the one on the 70 plus. And then for subject 2, we optimized the sequence to take advantage of the stronger gradients. You can see the main effects highlighted here in yellow. So the much higher gradient strength and slow rate allowed us to shorten echo time quite significantly. This was obviously a very important aspect for us looking at being confronted with such difficult B0 artifact affected area. But also the impulse gradient allowed us to reduce repetition crime quite a lot as well, which obviously helped us to get to much shorter scan times overall. In fact, we got under 10 minutes, a magical number, I think, which was very important also for our clinical collaborators because one of them would like to explore pediatric patients in the future. And here we can see the first result that we got from these two scans. So these are main raw diffusion images from our local system on the top and the NexGen system on the bottom. These are not the same subject, obviously, but you can still appreciate the considerably lower distortion in the raw diffusion data across the whole brain and the brainstem and posterior fossa in particular. The impulse gradient of the NexGen system essentially allowed us to get, as I said before, to clinically feasible less than 10-minute scan time and allowed us to reduce the echo time by 36%. Let's now look into the two nerves in more detail. So here we look at the zoomed in region of the brainstem and the calculated FA maps in the top row and the fiber orientation distribution functions on the overlaid on the bottom row. These were generated in MRTrix after ends-based motion correction and Gibbs ring removal. And we also used MRTrix for denoising. You can see that's the 70 plus results from our local scanner, and that's the results we got from the NexGen scanner. And we're currently looking at the trigeminal nerve, which is highlighted by the white arrows here. You can see that it can be identified on both 70 system, with the NexGen system being able to delineate the nerve bundle much further beyond the root entry zone, which you can see in the right arrow here. So we're very excited about this because it's the first time we've been able to track the nerve this far. Yeah, we can also see this from the tractography results here. So tractography was seated manually on the left side of the brainstem. You can see the reconstructed fiber pathways of the trigeminal nerve shown here in green. And these paths originate at the root entry zone at the brainstem and then extend outward along the pathway. And just this is like we've seen this before. This is the anatomy of the trigeminal nerve, and you can see that we are able to track well beyond the nerve entry, the root entry zone over here. You can even see a bit of the trigeminal ganglion depicted here. So next we looked at the auditory nerve, and in this slide we're comparing again the 70 plus on the left and the NexGen system on the right. The top row is again fractional anisotropy maps, and the bottom rows are fiber orientation distributions that we got from the CSD analysis. We focus again on the areas here that are shown with the white arrows, in which you can see the auditory nerve emerging bilaterally from the brainstem. These are visible on both data sets, but when we try to follow the nerve further along its course, we can see that we start to run into issues. The red arrows highlight areas where the signal drops out, particularly as the nerve moves laterally towards the inner ear, which indicates that we are still very challenged by B0 artifacts. Yeah, as a result, so even though the CSD analysis can identify the nerve close to its origin, the diffusion signal becomes unreliable if we move a little bit further along the pathway, which still makes it quite challenging to track this trajectory. And this brings me to the end of this overview. So as you can see, we've only just started data acquisition and we're still in the process of optimizing our parameters, but in conclusion so far, the trigeminal and the auditory nerve are important clinical imaging targets, particularly for conditions like trigeminal neuralgia and auditory neuropathy. Imaging these nerves is challenging just because of their size, location, and particularly all the air-bone interfaces and the proximity. Using the impulse gradients, we were able to shorten the diffusion encoding and as such echo time, which helped us to reduce distortion and allowed us to get high resolution acquisitions and very practical scan times. In our preliminary results, we could see that we are able to get much better signal and improved visualization of the trigeminal nerve, and we're able to track it beyond the root entry zone. At the moment, we're looking at optimizing the sequence parameters, and we're also looking to employ a PTX-based diffusion sequence that we are currently developing over here in conjunction with Siemens. But in the meantime, I would like to thank everyone involved, in particular the great team over at UC Berkeley, Alex Beckett and Alex Kegai, as well as Joseph Eriga and David, who've been really wonderful to work with, and we're looking forward to acquiring some more data soon. Thank you.